in between what? Qmax and Qmin. And regarding this point, it is equal to what? 0.02, right? So we have to check on this point over here, point B. And we also have to check on point C. The advantage of, or the one advantage point C has, it has what? It has a Qmax. Okay, so point B and point C, there's a possibility that the maximum shear stress will occur. It's not a guessing game. Okay, you cannot guess. Okay, you have to calculate. Okay, so let's look at point B first. Okay, so QZ at point B. So before I want to or consider, so we have to determine. Okay, we have to determine the Q over T ratio now. Okay, the bigger this ratio, the higher the what? The higher the stress. I repeat again, the bigger this ratio, the higher the stress. Okay, so let's consider point B. And we know the thickness for point B is twice of 0.01. So the thickness is equal to 0.02 meters. Okay, so Q Z at point B. So this is the web first. The width is what? The width is 50. The depth is 0.01. The Y bar, so this is 20, 30, 10. So 0.06 minus by 0.01 divided by 2. Okay, so this is the width, this is the depth, and this is the Y bar. So from here, we calculate the value. So it's 0.06 minus by 0.01 divided by 2 times by 0.1 times by 0.05 is equal to 27.5 times 10 to the power 6 meters. Then the QZ over T ratio is equal to 27.5 times 10 to the power minus 6 divided by a thickness of 0.02. Right, so 27.5 power minus 6 divided by 0.02 is equal to 1.375 times 10 to the power minus 3. Okay, so 27.5 power minus 6 divided by 0.02. Okay, so if we were to determine the shear stress, right, at point B will be equal to Vy over Izz. We know it's constant, but this value is 1.375 times 1.375 times 10 to the power minus 3. Okay, so now let's consider at point C now. Okay, at point C, and we know that point C, the thickness is equal to what? Is equal to 0.05 meters. Okay, it's equal to 0.05 meters. So we are checking this at this point, at point C, this is 0.05 meters now. Okay, so now we have to calculate the first moment of area at point C. So we know that QZ at point C is equal to 27.5 times by 10 to the power minus 6 plus. Okay, so because at point B, we consider at point B, I'm going to highlight, we have considered this section for point B already, right? We consider this section for point B, right? So point C, we just need to add the yellow bit. Okay, we just need to add the yellow bit. Okay, so the width plus by the width will be equal to 0.05. The depth is equal to 0.02. The Y bar is 0.02 divided by 2. Okay, so this will be equal to 0.02 divided by 2 times 0.02 times 0.05 plus 27.5 power minus 6 is equal to 37 point. Hold on, did I do it correctly? Hold on, I'm checking my calculation. 27.5 times 10 to the power 6. So 2. So the width QZ at the centroid. Did I? Hold on. I think I missed something over here. Yeah, I did. I do apologize. I'll tell you what I missed, okay? I only consider, I did not add the other part, okay? I was rushing. So can we go back to point B again? Okay, we clear this out. I did it wrongly because I forget to add another section, which is the web section at point B. Okay, so this over here is plus twice. So where I did not add up, when I did it the first time, I'll only consider here, which is not enough. Okay, I need to consider these two sections, which I forgot. Okay, my bad. Do apologize. So width, so twice width is equal to 0.01. The depth is 0.03. And the y bar is equal to 0.02 plus by 0.03 divided by 2. Okay, so this will be equal to 0.06 minus by 0.01 divided by 2 times by 0.01 times by 0.05. So this is still 27.5 plus by 0.02 plus by 0.03 divided by 2 times by 0.03 times by 0.01 times by 2 is equal to 21 times 10 to the power minus 6. And then this will be equal to 27.5 plus by 21 is 48.5 times 10 to the power minus 6 meter cube. Okay. So from here, I'll write down the ratio QZ at point B divided by thickness. So this is equal to 48.5 times 10 to the power minus 6 divided by the thickness, which is twice of 0.01. So this is equal to 48.5 power minus 6 divided by 2 divided by 0.01 is equal to 2.425 times 10 to the power minus 3. Okay, let me do it again. 48.5 power minus 6 divided by 2 divided by 0.01. Okay, 2.425. So the QZ, if you look at units, this is in what? Meters cube. This is in meters. So over here, in fact, you have a meter squared. So the shear XY at point B will be equal to 2 BY over IZZ 2.425 times by 10 to the power minus 3. Okay. So now coming back to the last part over here to find the first moment of area at the centroid, this is 48.5 times 10 to the power minus 6. Okay. So this will be equal to 0.05 times by 0.02 times by 0.02 divided by 2. So this is 48.5 times 10 to the power minus 6 plus by 10 times 10 to the power minus 6. So this is equal to what? It's equal to 58.5 times 10 to the power minus 6 meter cube. So you can see if I were to highlight the two values, right? QZ at point A is 48.5. At the center is 58.5 as expected, right? So the first moment of area at point C or at the centroid is the highest. Okay. So now is where we divide by what? Now we want to find QZ at point C, divide by the thickness now. And we know that the thickness is equal to what? 0.05. So 58.5 times 10 to the power minus 6. And then we divide by what? We divide by 0.05, right? So 58.5 power minus 6 divided by 0.05. Now this is equal to 1.17 times 10 to the power minus 3. Now you can see for yourself, right? So this is at point C, right? This over here, so the unit is still meter squared. This is at where? This is at point B. So you can see the ratio of QZ over T is higher at point B than at point C, yes or no? So if we were to write shear XY at point B or at point C, is basically Vy over IZZ, right? So this will be 1.17 times 10 to the power minus 3. So obviously from here, by looking at the coefficient or the QZ over T coefficient, you can see here. So maximum shear stress, so therefore, maximum shear stress will occur at point B. Okay, right? So you can now see the Q over T ratio, right? Okay. So this is based on Q over T ratio, right? The first moment of area is always fighting with the what? The thickness, yes or no, right? So this is where things get interesting by just focusing on the Q over T ratio. Okay, so now you will say, Eugene, so what, we have this value, or before we go into the so what, if now we are going to sketch, if now we're going to sketch, okay, again, I highlight that this is a sketch on the shear stress distribution. Yeah, I'll take this. We come here. Once we finish this sketch, we go for a 5 minutes break, okay? So if we were to sketch here, right, where things get interesting, I think it get interesting. So if this is the position of my centroid, right? So if this is the position of our centroid, and then this over here is our Y, and this is our shear. There are a few critical points. And this points is, again, I draw this location because the thickness changes, as you can see. Down here is one thickness. Over here is another thickness. And then you have another thickness over here. The thickness changes, right? And then you have thickness change from here. Okay. And your thickness changes again. And finally, so if we will sketch this, right, it will go like this. So we know that this is 0, right? And then you will have a step. The thickness changes. Then your peak, right? Then the thickness changes. Then you'll come down here. And then you do this. And then you do this. And you come here. Now we can see how your shear stress distribution looks like now. So we know that at the centroid, right, tau is not equal to what? Tau max. Okay, as I said, this is purely due to the Q over T ratio. Okay, what I propose, we take a 5 minutes break and we come back again.